Imagine for a second that you're a robot. Or, if that's too much of a stretch, just imagine you're a very stressed out human trying to get to work on time. You're trying to navigate the world. But here's the kicker. You rarely, if ever, have all the facts.
Right.
You don't know for sure if it's going to rain. You don't know if that red line on Google Maps is a car crash or just a baseball game letting out. And you definitely don't know if your car won't start because the battery's dead or because you were too tired to remember to get gas last night.
That is the fundamental problem of intelligence, isn't it?
What?
Reasoning under uncertainty.
It is the absolute worst. And that's what we're unpacking today. We're taking a deep dive into a concept called maze nets, or Bayesian networks. And frankly, this seems to be the secret sauce for how computers and, ideally our own brains, predict the future without needing to be all-knowing.
That's a great way to put it. To help us decode this, we're looking at a stack of lecture materials on artificial intelligence and probabilistic models. These come from Dr. Reza Abdali at CSU Channel Islands, adapted from a course at UC Berkeley.
It's interesting because usually we think of AI as this mysterious black box. But these lectures, they sort of peel that back and show us it's actually just probability. It's math trying to make sense of a messy world.
It is. The mission today is to look at these diagrams, which, at first glance, just look like a bunch of circles and arrows, and understand how they act as a map for reasoning.
Okay.
It's about how we can diagnose problems like that car breaking down or predict outcomes like insurance risks by understanding that while everything is connected, not everything is connected to everything else directly.
Which is good, because if I had to think about the entire universe every time I made coffee, I'd never get anything done. So let's unpack this. The lecture starts with a pretty massive problem. It talks about probabilistic models and the challenge of the joint distribution.
Right. This is the starting line. To function in the world, an agent, whether it's an AI or a person, needs to reason about unknown variables based on the evidence they have.
But the slides make a point that trying to map out every single possibility is just a nightmare. There's this formula mentioned, 2 to the power of n for Boolean variables.
Let's pause on Boolean for a second. That just means variables that are either true or false.
Yes or no?
Raining or not raining. Simple stuff.
Got it.
But here's where the too big problem comes in. Imagine you have a system with, let's say, just a moderate number of variables. Is it raining? Is it cold? Is traffic bad? Is the car working? Let's say you have just 20 of these.
20 doesn't sound like a lot.
Well, if you tried to create a table listing every possible combination of those true or false states, that's not a spreadsheet you can just open.
It's not.
That is a list with over 1 million rows.
Okay, wow. That escalated quickly.
And if you go up to 30 variables, still a tiny model for the real world, you're looking at over 1 billion rows. It becomes physically impossible to store, let alone learn from.
So it's like trying to list every single state of the universe just to decide if I need an umbrella. Like, okay, if the moon is in this phase and the price of tea in China is X, then it will rain.
That's the intuition. It's wildly inefficient. The slides explicitly say that this full joint distribution is way too big to represent.
So enter the hero of our story, Bayes nets.
Bayes nets are the solution. They're a technique for describing these massive complex distributions using simple local distributions.
I like the word local there. It implies we don't need the big picture all at once.
You've hit on the core concept. We don't need to know how everything affects everything. We only need to know how variables locally interact. If we understand the local physics, we can chain them together to understand the whole system.
So let's look at the anatomy of one of these. The slides have a section on Bayes net semantics. Visually, it's a graph. You have nodes, the circles representing variables like rain or traffic.
And you have edges, the arrows connecting them. It's what we call a directed acyclic graph.
Directed, meaning the arrows point one way, sort of cause to effect.
Yes, and acyclic just means you can't get stuck in an infinite loop. But the real magic happens inside the node. Each node has something called a CPT, a conditional probability table.
CPT. The slides describe this as a description of a noisy causal process. What does that mean, noisy?
Think of the CPT as the local physics of that specific variable. It just answers one question. Given the state of my immediate parents, the arrow's pointing right at me. What's the probability of me happening? The noisy part just means it's not a sure thing.
Okay, so if I'm the traffic node, my CPT doesn't care about the price of tea in China.
Yep.
It just looks at its parent nodes, maybe rain and accident. It just says, if rain is true and accident is true, then traffic is, say, 99% likely.
That's it. And by stitching these little local tables together, you can build incredibly complex systems without that billion-row headache.
Speaking of complex, I want to dig into the examples in the source material because they really show how this works. First, there's the car network.
This is a classic diagnostic model.
It's this web of ovals. You've got battery dead and no gas and fuel line blocked, and they all point downward to this one red node at the bottom. Car won't start.
Right. So imagine you're a mechanic AI. You observe the effect. The car won't start. You can't see the gas in the tank or the battery's chemistry directly. But the Bayes net lets you flow that information backwards.
So it's like Sherlock Holmes. The car won't start. That makes battery dead more likely. But wait, the diagram also has a node for radio works.
And battery dead points to radio works too. So if the car won't start, but you turn on the radio and it's blasting music.
Then the battery's probably fine, and the probability shifts over to no gas or starter broken.
Precisely. The network propagates that new evidence to rule out some causes and make others more likely. It handles the diagnosis dynamically.
That makes sense. But then there's the insurance network. And honestly, looking at this slide, it looks like a bowl of spaghetti. There are red arrows everywhere.
It is visually overwhelming, isn't it? You've got age, good student, driving skill, accident, medical cost. It's huge. But what strikes me is the story here. This feels like a map of how an insurance company judges you.
It effectively is. Look at the top left. You have age and socioeconomic status.
And age points to good student, which then points to driving skill.
Now, why would they link being a good student to driving skill?
I guess. If you get good grades, you're conscientious, you follow rules, something like that.
That's the assumption built into the model. The model says, we can't observe your driving skill directly, but we can ask for your GPA.
So the machine uses good student as a proxy. If your GPA is high, the probability of good driving skill goes up. And if that goes up, the probability of an accident goes down.
Your insurance cost goes down.
So when I was 16 and mad that I had to show my report card to get a discount, I was basically just feeding data into a Bayes net.
You were engaging with a probabilistic model, yes. And notice, even though that whole graph is huge, the calculation for your premium is just a chain of these little local steps. It's wild. But that whole game relies heavily on one concept, right? Independence.
Yes, independence is everything.
The slides bring up the coin flips example.
This is the baseline. If you flip 10 coins, the result of coin 3 has absolutely zero impact on coin 4. That's absolute independence.
Which is great for math class, but the slides have this quote, absolute independence is very rare.
Right. In the real world, things usually mess with other things, which is why the concept of conditional independence is the real aha moment of this whole deep dive.
Okay, let's break this down. Conditional independence. This is the idea that two things might be connected, but if we know a third thing, that connection might just disappear.
Or appear. It depends on the structure. The slides use a traffic example. Model 1 assumes rain and traffic are totally independent.
Which is a terrible model. Anyone who drives knows that's not true.
Exactly. So Model 2 is better. Rain causes traffic. There's an arrow from rain to traffic. Now this lets us use something called the chain rule to break down the probability, instead of that massive exponential table.
The billion-row one.
Yes. We can break the math down into manageable pieces. The slides mention it drops to something like O of n times 2 to the k plus 1.
Whoa, okay, talk to me in English. What does that mean?
It looks scary, but it's actually good news. Remember our billion-row table? That depends on the size of the whole world, n. This new formula says the difficulty of the problem only depends on the size of the largest immediate family of parents, k?
So instead of worrying about everyone at the party, I only need to worry about who's sitting at my table.
That is a perfect analogy. The computation scales with the local families, not the total population.
That is a massive shortcut. But the real fun starts when we look at the specific shapes these arrows make. The sources call them the canonical cases, the triples.
These are the logic gates of the real world. There are 3 main patterns.
I want to walk through each one because this is where the logic gets a bit trippy. The first one is the causal chain, or the cascade.
Visualize this. Low pressure causes rain. Rain causes traffic. Low pressure, arrow to rain, arrow to traffic.
Okay, like water flowing downhill. So is low pressure related to traffic?
Yes. If I tell you the pressure is dropping, you should probably bet the traffic will be bad later. The information flows through the chain.
But here's the twist, the conditional part. What if I already know it's raining? I'm looking out the window. It is pouring. Does telling me, oh, by the way, the pressure is low, help me predict the traffic any better?
No. It does not. You already have the direct cause. The information about the pressure is now redundant.
So the evidence of rain blocks the influence of pressure.
Think of it like a valve. Observing the middle node, the rain shuts the valve. Information about pressure can no longer flow through to traffic.
Okay, so knowing the middle link breaks the chain. That's case 1. Now, case 2, common cause.
The parent. The example here is a project due date. If a project is due, it causes two things. Forums are busy and the lab is full.
So 1 parent, 2 children. If I walk into the building and see the lab is full, can I guess that the online forums are busy?
You can. Because if the lab is full, it's probably because a project is due. And if a project is due, the forums are probably also busy. They're correlated.
But apply the twist. What if I know the project is due? I have the syllabus.
When knowing the lab is full, it doesn't tell you anything extra about the forums. You already know the root cause.
So again, observing the middle node, the common cause, blocks the path. It separates the two effects.
Exactly. But now, we get to the third case, the V structure, the collider. And this is where things get really counterintuitive.
The diagram here is rain points to traffic and ball game also points to traffic.
Yeah.
2 arrows pointing into one node.
2 independent causes sharing one effect.
So first question, are rain and the ball game correlated?
No, they're independent events. Whether it rains has nothing to do with whether the Dodgers are playing.
Okay, but here's the twist. What happens if we observe traffic? We're stuck in a jam.
Suddenly, they are related.
Wait, hang on. You're saying because I'm stuck in traffic, suddenly the rain and the baseball game are linked? How does that work?
It's not a physical link, it's an informational one. It's a phenomenon called explaining away.
Explaining away.
Imagine you're stuck in that traffic. You're wondering why. It could be rain, it could be a game. Now you look out the window, you see blue sky, no rain.
Okay, so I know it's not the rain.
Since you know there is traffic and you know it's not from the rain, what happens to the probability that there's a ball game?
It has to go up because something has to be causing this jam.
Exactly. The causes are now competing to explain the effect. If one explanation fails, no rain, the other one becomes much more likely.
So observing the effect, the traffic actually opens the valve between the two causes.
Yes, this is the only case where observing the middle node activates the path. Before you knew about the traffic, rain and baseball were strangers. Once you see the traffic, they become rivals in an explanation game.
I need to let that sink in. The act of knowing the result connects the causes. Can we try another example? Because my brain is still buffering on that one.
Sure. Let's say being late. 2 things might cause your coworker, Bob, to be late. 1, his car broke down. 2, he overslept.
Car breakdown and oversleeping are usually independent things.
Right. But Bob walks in at 10 a.m. He is late. We observe the effect.
Okay, Bob's late.
Now, you see Bob holding a grease-covered tow truck receipt.
Okay, so his car definitely broke down.
Do you still think he overslept?
No. I mean, he could have, but I don't need that explanation anymore. The car explains it all.
Exactly. Finding out the car broke down makes it less likely that he overslept. You have explained away the other potential cause. Observing the lateness is what linked the two causes in your mind.
That actually makes total sense. If I have one good excuse, I don't look for another one.
That is the logic of the V structure. And that whole process checking which paths are active and which are blocked is called deseparation.
Deseparation sounds like a bad celebrity breakup.
It stands for directed separation. It's a formal method to look at any graph, no matter how messy that insurance web is, and determine if variable A is relevant to variable B, given what we know.
The slides talk about active paths.
Think of it like a circuit board, or those pipes we mentioned. A path is active if information can flow all the way through. It only takes one closed valve to block the whole path.
And Bayes nets let us calculate this flow with real numbers. The lecture ends with the alarm network example, which does just that.
Right. You've got a burglary, an earthquake, an alarm, and 2 neighbors, John and Mary, who might call you.
Burglary and earthquake are the causes. They both point to alarm. That's our V structure again.
Correct. An alarm points to John calling and Mary calling. Those are causal chains.
The slides show how we can handle that noisy logic here. The table says if there's a burglary, the alarm goes off 95% of the time. But if there's an earthquake, it only goes off 29% of the time.
And even if there's neither, there's a tiny chance of a false alarm. A butterfly lands on the sensor or something.
So the Bayes net allows an agent to calculate something really specific. What is the probability of a burglary, given that John called?
It's not just a guess. It calculates it by flowing the probabilities through these open and closed paths. John calling is evidence. That activates the path up to alarm. And alarm.
It activates the path up to burglary, but it also activates the path to earthquake, right?
Right.
Because of that V structure.
Yes. And the system balances all these probabilities to give you a single precise number that represents your uncertainty.
So what does this all mean for us? Why should we care about this stuff unless we're actually coding a robot?
Because this is how we scale intelligence. We started by saying we can't know everything. Bayes nets allow us to build complex models out of simple local probability.
It's efficiency.
It's feasibility. This is how diagnostic systems in finance and robotics and medical diagnoses handle the real world. A robot doctor doesn't need to know the phase of the moon to diagnose a cold unless there's a specific causal path linking them.
It effectively tells the robot what to ignore.
Yes. In a world of information overload, knowing what doesn't matter is just as important as knowing what does.
That's deep. It's about filtering the noise to find the signal.
You know, there's a quote on one of the slides, models are always simplifications. And a Bayes net is largely defined by the arrows that are missing. The connections we decide just aren't there.
The empty space defines the structure.
It makes me think about that V structure again, the explaining away concept. Right in the ball game are independent, but we connect them when we see the traffic.
Where are you going with this?
I wonder, in our own lives, how often are we bad Bayesians? How often do we create false correlations where there are none?
Like what?
Think about, I don't know, the workplace drama. You see two colleagues, Alice and Bob, and they're both in a bad mood. That's the effect you observe.
The traffic.
Right. Now, Alice and Bob might be grumpy for totally independent reasons. Alice spilled coffee on her shirt. Bob's team lost last night. But because you observe the shared effect, the bad mood in the office, you start to assume there must be a shared cause. Well, the boss must have yelled at both of them. Or you put them in competition. Did Alice say something to Bob?
We create a V structure where there shouldn't be one. We invent a connection because we can't handle the coincidence.
Exactly. We force a relationship between two independent things just because we're stuck in the middle observing the outcome. Maybe sometimes we just need to remember the independence.
So the lesson is, don't assume the rain and the baseball game are talking to each other just because you're late for dinner.
That's a pretty good rule to live by.
Thanks for diving into the math with us. This was actually surprisingly clearer than I expected it to be.
A pleasure.
See you next time on The Deep Dive.